Hello and welcome back to General Chemistry 2. My name is Daniel, and in this video we're going to be exploring the topic of electrochemistry, which we'll find out is just going to be any kind of chemical reaction that involves the production or consumption of electricity. So common applications of this could be in batteries, being the most prominent probably, something like fuel cells, or even solar electricity applications. We'll see a few of the examples as we go through this video. So the first thing we'll do is we'll define what an electrochemical reaction entails. So as I just said, an electrochemical reaction is just one that involves the transfer of electrons, or the production of electricity, which is electrons. And so in order to generate electrons, there's going to be an oxidation-reduction reaction occurring. You'll remember that we went over those in detail in General Chemistry 1. So you have an oxidized species which lost electrons, you have a reduced species that gained electrons. So we can create a system that utilizes this transfer of electrons to create electricity, and that's known as an electrochemical cell when you have an operation like that. So for example, something like a battery would be known as an electrochemical cell because it has an entire system within it. So I mentioned the examples of electrochemical reactions. Like I said, there's batteries. You can have metal plating, like if you want to coat a metal with some other metal. And something like metal corrosion, or something like you'd see in rusting or the disintegration of marble via acid rain. Those are electrochemical reactions. So how we'll begin this is we're going to review balancing reduction and oxidation reactions. So just to review the terminology, remember that we can split any kind of redox reaction into two half reactions. First, there's a reduction reaction in which the species gains electrons, and then there's the oxidation reaction in which electrons are lost. And you remember that the reduced species is the oxidizing agent, and the oxidized species is the reducing agent. So the other thing we have to be able to do is we're going to have to be able to balance our redox reactions. So hopefully you remember this from General Chemistry 1. If not, we'll go briefly into reviewing how to go about this. But the basic setup is like so. We're going to assign oxidation states to all the species. From that, we're going to determine what species are oxidized and which ones reduced. Using that, then, we'll create our half reactions. So I'll write out those, and then finally we're going to balance the half reactions based on the fact that the number of electrons lost by the oxidized species has to be the same as the number of electrons gained by the reduction species. In 5 and 6, we just have the details of doing it in an acidic medium or a basic medium. Generally, we're not going to get much into that, but that's just there for your review purposes. And then finally, we're going to just add the half reactions that we balance together to get our final reaction. So, see if you remember how to do a redox reaction. Just balance this pretty simple reaction here. So I'll give you a minute to pause the video and do that. Alright, so the first thing we'll do is we'll assign oxidation states. That's pretty straightforward here. Our metals both start at 0, and we have our ions. So we see that aluminum goes from 0 to 3 in terms of its oxidation states. So that means it lost 3 electrons. Remember that losing an electron makes a positive charge. So we can write then that our reduction reaction is aluminum goes on to form aluminum plus 3 and loses 3 electrons. On the opposite end, we have that copper plus 2 is going to gain 2 electrons to form copper metal. So those are our two half reactions, but now we have to balance them in terms of the electrons that have been transferred. To do that, we'll multiply the first equation by 2 and the second one by 3. That'll give us a total of 6 electrons. So if we write those out once again, we'll get 2 Al metal goes to 2 Al plus 3 plus our 6 electrons. The oxidation half reaction will look like this, with 3's in front of everything. And then finally, we can just add them together. The electron numbers will cancel since they're on the same on both sides. And we're left with our final balanced reaction, which looks like so. Okay, so That was pretty straightforward. All we had to do was just balance out the number of electrons that are transferred between each species. We'll see that that's going to be an important point to do when we start getting into solving problems for electrochemical cells in particular. Okay, so with that then, let's introduce the most basic electrochemical cell, which is known as a galvanic cell. So there's a lot going on here, and I'll explain this by basically going into each part of this in detail. First, let's define a few terms. There's two sides to a galvanic cell. There's what's known as the anode and the cathode. The way these are distinguished is that oxidation occurs at the anode, whereas reduction occurs at the cathode. So you see here that we have zinc on the left side in our anode, and we have copper on the right in our cathode. And then the half reactions are as such. We have the oxidation of zinc here in the anode, and we have the reduction of copper over here in the cathode. So what's happening in each of these? So in the anode, we see that zinc metal is forming zinc ions. So that means parts of this zinc bar are going to go into solution and form Zn+2. On the other hand, on the cathode, we see that the ions are becoming metal, and so they're going to get reduced into the copper metal. So what that means is over time, as this circuit continues, the zinc bar will disintegrate and the copper bar will grow larger and larger until the reaction has no more fuel with which to go. So now a few other points. Since we have this thing here called the salt bridge in between and connecting the two compartments. This is it's not having the liquid flow between them, it's just a bridge with salt in it, hence why it's called the salt bridge. So the function of the salt bridge is to maintain charge balance. What does that mean? So in the anode, we see that we're producing these extra new positive cations. So in order to maintain charge balance, the some kind of negative anion, in this case chlorine, has to migrate into that solution in order to make sure that the charges remain balanced in it. And likewise, on the other side, in the cathode, we have that copper plus 2 is becoming copper metal. And so that means that we're losing positive cations over here. And in the opposite way of the anode, that means that positively charged species are going to migrate into that solution to restore the balance of charge. In this case, K+. So on the cathode, we were losing positive particles. In the anode, we were gaining positive particles. And that's the function of the salt bridge here. And then finally, we have our most important part, which is the circuitry itself. So what we see is that in the anode, in this oxidation, electrons are released. The way that this electrochemical cell produces electricity, and so that we can utilize that electricity, is there's going to be a wire connected between the anode and the cathode. So what happens here is that in the oxidation of the anode, electrons are released. These electrons flow through the wire to whatever we want to power, in this case the light bulb, and eventually they end up in the cathode, where we see that they participate in the reduction reaction itself. So this is kind of like one big circle. You have electrons traveling from the anode to the cathode. You have negatively charged salts and positively charged salts going to the anode and cathode respectively in order to maintain charge balance. So there's a lot of motion of species. One of the easiest ways to analyze a galvanic cell is by looking at the anode and cathode first separately as what is known as half cells. So let's take an in detail look at the anode first. So as we said, oxidation is occurring on the left side of this galvanic cell, and that's the oxidation right there. We're bringing zinc metal into zinc ions. So what will happen then is that we see that these electrons then are released by this reaction, and they're going to travel to the other side in the cathode. We also said that the negative